The objective of this part of my presentation is to show how you can do space union of two data sets that have different spatial exposure. So we have data sets that have been merged with a sensor and other the what has been done by hand. And there are several functions on how to do this. We're going to show you two different types. The first one is by using an ST joint function, and the other one interpolation function. So this is data set that we're going to join. The first example that we'd have would be this function without specifying the conditions of this joint. So since there's no information, it shows you as not available and throws an error. The other example, which is the simplest method, consists on doing a union by using a criterion. You're going to choose the closest option. For every observation, we have a soil sample. Now we're going to identify the observation that's closest when using the sensor rake, and the data can be validated by that. That's a very commonly used methodology. Another option that can be used is to set a maximum distance. For example, we're going to join the ones that are within a distance of 5 meters. And in that case, not all observations are going to follow this rule. There's probably going to be a few that are going to be further to the sensor. So it does not identify any of them. And there's another option that's a little bit more robust and can be used, which consists on using buffers. And the idea is that in every place where we've taken an observation by hand, we are going to create a circle in an area around of 20 meters. You can use another distance depending on the data set. And after that, we'll create these circles around every observation. So once we've got those circles in place, we are able to calculate an average of the values that are within the circle. So there's a few circles here. We take an average, and that's the value that's going to correspond to the soil observation. The other means of observation. Once that is done, you use the aggregate function and you calculate the mean in order to produce the data. And once you've got the means, they are aligned by using that function, the cbind function, with the original data set that has been taken by hand. So this is the data set of the aggregates, and this would be the samples that were taken by hand. Now we're going to show another example which requires the use of interpolations. Interpolations are predictions made in zones where we have not taken any measures. And somehow similar to taking an average. It's similar to what was done with the buffer. What's mostly used would be inverse distance. And what this method does is to get an average of the values that are close in the same way that we did with the buffer, but we're going to give a different number to every observation. The observations that are closer are going to have more weight compared to those that are further. So this allows to have another average. This is we're using a library that's called Geostat, and with this library we can calculate the interpolation of every value by using a model that shows the variable and it's equal to 1. And by doing this, you can calculate a surface with the interpolation of electrical conductivity at 30 and 90 centimeters. Something else that can be done is it's try to define the value out of these variables in a new data set. And that's the data where we are going to take next week. So you run those predictions, and once the predictions have given a result, we assemble all of them in a table by using the cbind function. So this is the original data, and then we have the predictive values. And this is a way that you can to create a new data set like this one. And this is the way it looks like. And the same way, you can use a geostatistical model. And with this model, what we're going to do is to use a semi-biogram. And these geostatistical models, we've already explained them in other modules, or you're probably going to see them very soon. And what we do with these methods is to use the information of the semi-biogram using the spatial structure to give that differential weight. So we're going to give more weight to the observations that are the closest and less weight to the ones that are the furthest. But things will change depending on the biogram. So once we've identified the function of the biogram, this will enable us to do a preliminary calculation of the model, and you get an algorithm that calculates and adjusts this biogram, which is the one that you're seeing here. So once we've got these models in place, we can use them to do predictions. So once again, we create two areas, two surfaces that are interpolated, that are images, and by using predict. So let's say we're going to use this data set that we created with the predictions, and we are going to see how they behave in the places where we taken the soil samples from. So once this has been done, we can assemble everything. We've got two sets of predictions, and then we assemble all of the values and include them in one table that allows to visualize which would be the predictions of the places where we've estimated these semi-biograms. So this is a summary of the different methods that we are covering. We've already spoken of two methods by using the join function, and then two others by using interpolations. Now we are going to talk about some criterions for establishing these patterns. The codes that you're seeing right now are examples that were developed by Agustin Aleso. He is one of our postdoc students here.